This is it. This is the big day, the day we finally get to talk about the user-defined function block. Before we do, let's review some of these system variables, the analog to digital hardware, and the scalar function, because these are some of the things that we are going to pull into and encapsulate within the user-defined function blocks. System variables. On a scale of 1 to 10, I would put this first scan somewhere up there around about a 9. This is something that you're going to need to use in your program. It is a one-shot, which means it's a pulse that's active for one program scan. This particular variable will be active for one and only one program scan. It will be active on the first program scan, as suggested by the name. You'll use it to initialize variables. This is a typical application. You can see that first scan variable used here on a normally open contact. On the very first scan, which is as soon as the machine is powered up or as soon as it's put into the run position, this will close. When it does, this move instruction will move this initializer, whatever real value you decide is important there, and it will store it in this memory location called real and important. From there, your program will start from a known position with known values stored in those memory locations. The scan count is used to count the number of program scans that have occurred since the device was powered on. With this knowledge, you could measure the performance of your program. This is a relatively easy thing to do. You could turn on the PLC, let it run for 5 minutes, come back and look at the scan count. You can then do a division and figure out how many scans you have per second. From there, you can ask yourself if that's good enough for your program or if your program needs some attention. As a side note, if your timing is that important, you may want to consider using interrupts. This is a mechanism that allows the PLC to execute a small piece of code with a very rigid time schedule. So you can rest assured that if you have a control system that must run every 100 milliseconds, that you will be back into that piece of code every 100 milliseconds. You could look at it this way. These interrupts interrupt the normal flow of your PLC program, and what they do is they vector over to the piece that you've specified, and they make sure that it has priority over everything else. That's something to look forward to next semester. The next variable is system cycle date. This is one of the most useful memory locations you have because it allows you to track time. The cycle date tells us the number of milliseconds the PLC has been running. It has a type time that tells us the elapsed time since the first program scan. Behind the scenes, this is used by the built-in timers, such as time on, time off delay, and your time on, off delay timers. You can also use it to construct your own timers, as we saw in a previous video. But be careful with this variable. We mentioned that it counts milliseconds, but it's only 32 bits. And if you start counting milliseconds using a 32-bit counter, you're going to find out that you can only get to 1,193 hours, 2 minutes, 47 seconds, and 294 milliseconds. At that point, you wrap round to 0, which means if you're not careful with this, you can have a fault, a runtime error, once every 49.7 days. That may not seem like a big number, but that's a service call 7 times a year. And over the life of the machine, which can be decades, that ends up being a very expensive bug if you don't catch it. The next topic on our journey today is analog inputs. For our conversation, we are going to focus in on the plug-in modules, the IF2 and the IF4. The IF2 is a 2-channel device, and the IF4 is a 4-channel device. Each one may be configured as a 0 to 10 volt DC input, or as a 4 to 20 milliamp input. You should know that these devices actually do measure 0 to 20 milliamps on that current input, but by convention we describe it as a 4 to 20 milliamp input, where 4 is 0 and 20 milliamps is full scale for that particular instrument. The connections will take one of 2 forms. We'll let this be the boundary of the PLC. The sensor will be connected to ground and some power supply. We'll call it 24 volts here. 2 wires will leave the sensor and enter the PLC, where they come across a 220 k ohm resistor. That is the input impedance of the voltage sensor. There's a ground, which goes to the system ground of the PLC, and then an analog to digital converter, which presents as 16-bit. From there, it goes to the sensitive logic of the PLC, including the FPGA and the microcontroller. A sensor with a 4 to 20 milliamp output would have a similar schematic. Again, we need a ground and we need a power supply to operate that sensor. Once again, we have 2 wires that enter the PLC, but this time the resistor is much lower. It's actually 250 ohms. Like its voltage counterpart, we head off to an analog to digital converter, which presents itself as 16 bits to the FPGA and microcontroller. If we look a little closer, we can see that the range of values that are valid for this ADC go from 0 to 10 volts. There is a similar situation here, except this time the voltage, as seen by the ADC, will go from 0 to a max of 5. And to understand how that works, you have to consider Ohm's law in this particular resistor. If the sensor has a maximum output of 20 milliamps, the voltage as measured at the ADC will be 250 by 0.02. So the voltage on the ADC will equal 5 volts. That's a fact that may prove useful one day as you actually physically measure the inputs and outputs of these sensors. For example, if you put an amp meter here, if the sensor was at full scale, you would expect to measure 20 milliamps. But maybe you don't want to go through all that effort of breaking the circuit and installing a current meter. Maybe instead you just want to measure the voltage. Well, if this device was full scale at 20 milliamps, this voltmeter would read 5 volts. And that is on the face of the PLC itself. 5 volts is full scale. You should know that the IF2 and IF4 modules are not isolated. These grounds are tied together. They're also tied to the PLC ground, leaving on the return line connected to the PLC power supply. So your analog system, your power supply, and your PLC are all tied together, which can create some interesting challenges when you have your sensors far away from the PLC. If you're not careful, you can establish what's called a ground loop, where you have current that is flowing between grounds. If you have a ground loop, you can be sure that it's going to magnetically couple noise into the main line leading from the sensor to the PLC. As a function of time, this voltage right here will no longer be smooth. Instead, what you'll see is noise that rides on top of it. Noise that can actually degrade the sensor performance. For now, just understand that this problem with noise exists, and as a rule of thumb, it gets worse the further the PLC and the sensor are physically located relative to each other. Let's take a look at this analog to digital converter from a different perspective. The input is an analog value that varies from 0 to 10 volts DC. The output is a digital word that varies from 0 to 65535. And there is a linear relationship between the two. Mathematically, we would say f of x is equal to mx plus b. The slope is equal to 65535 over 10, which means the slope has a value of 6553.5. The y-intercept is equal to 0, which means our equation f of x is equal to 6553.5x. And we can test that at full scale. If x is equal to 10, our output will be 65535. Know that this value right here is a 16-bit. It's actually 2 to the 16 minus 1. We have the same situation for the current. We have 0 to 20 milliamps scales linearly from 0 to 65535. Here's what we mean by scales linearly. Mathematically, we describe it the same way. F of x is equal to mx plus b. The slope is equal to 65535, and we'll use milliamps in this case. So our slope is 3276.75, giving us an f of x of 3276.75x. It's important that we use this value at one particular point. What is the corresponding value at 4 milliamps? So f of 4 is equal to 3276.75 multiplied by 4. You'll find that f of 4 milliamps is equal to 13107. So 4 milliamps corresponds to 13107. That's a number that you're going to want to remember because we're going to use it a couple times today. For example, In this application, we have a tank. We'll let this tank have a height of 33 feet. On top of the tank is a sensor. This sensor has been calibrated so that 0 feet corresponds to 4 milliamps and 33 feet corresponds to 20 milliamps. That gives you a linear relationship for the sensor, where 0 to 33 feet scales from 4 to 20 milliamps. Again, linear relationship there. The analog to digital converter inside the PLC will see it this way. It'll see that a 4 to 20 milliamp signal scales linearly to 13107 to 65535, which is fine, but if you are watching this human-machine interface, that's not very useful to you. What you want to know is the tank height. So we need to do yet another conversion. This time we're going to take 13107 to 65535 and map it back to 0 and 33.0 feet. So there's 3 transfer functions. We have the sensor, where 0 to 33 feet scales to 4 to 20. And that's this wire right here. We have the operation of the analog to digital converter inside the PLC, where 4 to 20 milliamps scales to 13107 to 65535. And then finally, we have an operation inside the PLC called scaling, where we take the 13107 65535 and convert it back into a type reel that goes from 0 to 33 feet. Since this is such a common action, the folks at Allen Bradley have made it real easy for you. We're going to start with our program in map, where we take the actual output of the analog to digital converter, I/O, slot 1, analog in, channel 00. We run that through an any to reel, and we send it to something called global type reel raw tank level. Since it's a global variable, we can now jump to our program control, and we will use the scalar block. There's quite a few inputs here. I think we better take a second look at this to see if we can make some sense of it. The input of the ADC had a 4 milliamp signal. That scaled to 13107. Full scale of 20 milliamps went to 65535. What we want is a value that goes from 0.0 to 33.0 feet. So our input min is here, our in max is here, this is our min out, and this is our max out. And now we can go over here and add those values. So our input is GR raw tank level, which we got right here. By the way, remember the scalar works on type reels. That's why we needed to put this as a type reel here. Input min, I believe we said that was 13107. Input max, 65535. Our output min is 0.0, and our output max is 33.0. I believe you got to put zeros here as well, because these are all type reels. And when all is said and done, we'll have our tank level. going from 0 to 33 feet. If we were to do this manually, we said f of x is equal to mx plus b. Could you figure out those values? Of course you could. M is equal to 33, so rise over run. Our run is 65535 minus 13107. So our slope is 0.000629435. And now we can use the point slope intercept form. So y minus y1 is equal to m by x minus x1. And I choose this point right here. So that's y minus 0 is equal to our slope, that's 0.000, what was that, 629435 by x minus 13107. So we end up with y, which is our f of x if you prefer, is equal to 0.000629435 minus 8.25. That equation is not too bad. In fact, you could build it in ladder logic yourself. So we take our gx raw tank level, which is x, which I forgot right there, and we multiply that by 0.000629435. We multiply, and we store the values in a location called real temp. Again, that's this part of the operation here. We've multiplied our input, which is the tank, by that slope. The real temp is then brought down to the next rung, where we subtract off 8.25 and put the result in real tank level. Let's take another look at those steps. We started here with a transfer function where 13105 to 65535 scales linearly from 0 to 33 feet. We calculated the slope of the line. We then used the point slope intercept form to calculate the equation of the line. We moved on, and I forgot to put the multiplication here because it is that number multiplied by x, and then we subtract off 8.25. Then we built the ladder logic. Here's the multiplication to perform this operation, and here's the subtraction to perform this operation here. Not so bad. But what if you found yourself in a position where this fancy thing called scalar didn't exist? Could you build it yourself? And this is the same question we asked with our timers and with our counters. Can you scratch build these things? And I propose that we can, and I think it would be very useful if we spent the next 5 or 10 minutes actually doing that. So we are going to build what's called a user-defined function block. We are going to construct the scalar block. To get started, we need to calculate the slope of a line. We could define that as in max minus in min divided by out max minus out min. So that's rise over run. As far as ladder logic is concerned, there's a subtraction there, there's a subtraction there, and there's a division. So you're looking at 3 different blocks. We also need to calculate this as y minus y1 is equal to m by x minus x1. There's your point slope. This would be the output minus the output minimum is equal to the slope by the input minus the minimum input. Again, we chose a particular point. Which point did we choose? We chose that point right there. So this is in min. In max, we have output min, and we have max output with that value right there. If we carry this out completely, we would say this is real out is equal to real slope by real in minus real in max plus real out min. We're going to jump to connected components in a moment, but just recognize this pattern. There's a subtraction and a division to find our slope. As far as our output is concerned, we have a subtraction, a multiplication, and a addition. The slope is calculated in the second rung. You see this first value here is a subtraction. That's the numerator. This value is a subtraction. That's the denominator. So now we have the numerator divided by the denominator gives us the slope. The third rung is the output rung. We mentioned that there was a subtraction, then a multiplication, and then an addition. Now, you're looking at something that you haven't seen before. This is a function block. You'll notice we're down here in the user-defined function blocks, and we're dealing with function block scalar. You didn't even know you're looking at it because it looks just like ladder logic. However, if you click here and you go to parameters, you can see how this block is put together. We've defined these inputs. We've defined these outputs. We have these variables inside that are not accessible to other entities outside of this function block. And again, the code itself looks identical to anything that you've played with before, right down to the local variables, which here are defined as type reals and type booleans. There you have it. That is what a user-defined function block looks like. It looks like any other piece of ladder logic code that you've played with. The difference is that you've defined a box. You've defined very clear boundaries from which this code operates. You have inputs, you have outputs, and most importantly, you have behaviors. These function blocks are very easy to use. We'll insert a rung below, then we'll search for function block. Looks like there's two of them I built here, so there's this one called scalar. We'll drop it here, and then you connect it up. The function block appears like any of the other built-in functions that you've built in the past. There's another nice feature about function blocks. You can export them, and you could share them with a friend if you wanted. So in rung 2, we showed how to instantiate a block. Let's see what they look like when they run. To get us started, I've already preloaded some of these variables. And the way you do that is you come here, and under the initial value column, you add the numbers that you'd like to see. So again, there's the 13107, 65535, 0, and 33 feet. Our input right now is set to 0, and our output is recorded as negative 8.25 feet. Well, that's not good. That would be an indication that you have a broken wire. So let's connect our wire back up, and we'll set this R in to 13107. And when we do that, we see the value goes to 0. If we go full scale, 65535, we should see 33 feet there. And if we go somewhere in the middle, say 45,000, there you are. You're at about 20 feet. For troubleshooting purposes, you can look inside an instance of a function block that's running, and you can see what's going on inside. At this point, we have to get really fussy with our terminology. What you're looking at is program scratch scalar. On that program, on rung 1, we have instantiated one of the user-defined function blocks called function block scalar. It came from this part of the program here where we talked about, or we constructed, a block called scalar. We can look inside an instance of an operational block. This is what we see. We can see how everything is connected. We can see all the inputs and outputs and all the intermediate values. If we go over here to the block itself, the one that we built, there's nothing there. This is not an instance of the block. This is a definition of the block. Again, if you want to see what's going on, you have to look at an instance of the block. If we'd had another instance, for example, we're going to add a rung and we're going to instantiate another block. And then if we connect it back up, we would find that these are two very different things. They have different inputs. So you could see if we'd opened it up that there would be different values on the inside. If that was confusing, we'll clear it up in the lab. But I think you can see the utility of this. We've taken this complex piece of code. We have wrapped it up into a nice, easy-to-use interface that we can use and reuse and share as many times as we'd like. Let's go back to the blackboard and see if we can build another one of these. This time we're going to build something called a time interval counter. This is actually a piece of test equipment that you could buy. It's a box with a display. It has an input A and an input B. There's typically a selector switch here. And that selector switch can be in one of two positions. It can be in a rising edge or a falling edge. So rising edge or falling edge of B. And the box can perform many different functions. It can calculate delta time from A rising edge to B rising edge. If you change those switches, you could also go and calculate delta time for A rising edge to B falling edge, or the period. You could go A rising edge to A falling edge, or many other combinations depending on where these switches were set. You could calculate the frequency or even the duty cycle, where a duty cycle is a ratio of time on to time total, which looks like a really good exam problem. Anyway, let's focus in on this piece right here. Let's build a user-defined function block to calculate the rising edge of A to the rising edge of B. Function block time interval counter rising edge of A to rising edge of B. Enable input A, input B, Boolean new trigger, type time delta, Boolean busy, Boolean A trigger and Boolean B trigger. In the style that we've been using for quite some time, we would describe inputs. That's all this. We would describe outputs. That's all that. And now we talk about behaviors. Our first behavior is only operate when enable is true. We want to calculate delta time as the time difference between rising edge A and rising edge B. Type time delta captures the time difference between rising edge of A and the rising edge of B. We want a clean, crisp update of time delta to correspond with when we are finished counting. And we'll finish counting when the B input goes high. Graphically, we end up with something that looks like this. We have input A. There's the rising edge. We have input B. And there's the rising edge of B. What we're interested in is this time difference right here. How much time has passed between the rising edge of A and the rising edge of B? We have an output called busy. We want busy to be low until it detects a rising edge of A and stay high until it detects the rising edge of B. So it's busy while it's calculating the time difference from A to B. We have outputs A trig and B trig. We're going to let this be A trig and B trig. A trig will just be a pulse that coincides with the rising edge of A, and we'll let B trig be a pulse that corresponds with the rising edge of B. We have this output called new trig. We want that to be low until new data is available. You could think of this as the signal to the next block in the line that says, hey, I've got new data. Speaking of new data, that's time delta. We would expect that to stay constant until the rising edge of B, at which point it'll transition to the new data. For example, we might start with a value of 1200 here. And after the transition, this might be 1100. Okay, but either way, we transition all of these things at the same time. If it's all the same to you, I'm going to leave it at that. I'm not going to fill out the rest of these behaviors. I think this timing diagram is sufficient for our needs. The code's not that bad. On rung 1, if not enabled, reset busy. On rung 2, if enabled, now here's something new. This is a pulse contact. So this is a rising edge pulse contact. It's the same as putting a normally open contact followed by an R trig. They do the same function. So if enabled and there's a rising edge on A, capture the system cycle date to this variable called A, trigger A output, and start the busy or latch busy. On the next rung, if enabled and there's a rising edge on input B, capture the time, send the B trigger, reset busy, and send that new data is available. Next rung, if enabled and there's a rising edge on B, calculate the time delta as B minus A. Let's go back and forth a few times just to make sure we have everything. On the rising edge of A, send a trigger pulse. Latch in busy. If enabled, on rising edge of A, send the A trigger pulse. Latch busy. On rising edge B, send a trigger pulse. Release the latch and signal that new data is available and actually update the data. On rising edge B, assuming you are enabled, capture the time. Here's the trigger pulse for B. Here's the releasing of the busy latch. And here we are sending that new data is available. On the next line, we actually perform the calculation, updating our delta output. The user-defined function is defined with these parameters. Here's the inputs. Here's the outputs. And these variables are used internally to do the calculations. That user-defined function block is instantiated here. And let's go ahead and run it. This is an instantiation, so we can open it up and see what's going on inside. Right now, we are waiting for enable to be set. The only thing that's moving in here is the system cycle date, and that will always be moving because the PLC simulator is indeed running. Let's go up one level. We will enable our time interval counter. And then you'll notice there are two push buttons here defined as global Boolean push button A, global Boolean push button B. If we activate A, immediately this goes to true. So busy is now true. By the way, you'll never see a trigger in connected components, so we don't know if A trig and B trig have functioned. However, if we look inside, the fact that this is busy means that this guy right here, this A, must have activated. And being as these are in parallel, we can be pretty confident that A trig has indeed operated. You'll notice there's a value in time A. That was the system time when A rising edge occurred. So now we come back here, and we can turn A on and off all we want. It's not going to make any difference because we're only looking for a rising edge of A, and then we stop on the rising edge of B. So as soon as I push this button, you should see busy goes to false and time delta should update. There it is. So 13 seconds. If we go back inside, we should see that busy has been reset and we are armed and ready for the next rising edge of A. Here's a rising edge of A. Again, doesn't matter how many times that occurs. Nothing will move. We turn off B, and on the next rising edge of B, this should go false, and we should update our time. There it is. I trust that was a useful discussion for you. You got to see two different user-defined function blocks, and I think you'll agree that these are things that you get to build once, troubleshoot, save, you can share them, you can build a library. The hope is that all of this will save you time. The more things in your library, the faster you'll be able to implement the code because you don't have to build it from scratch every time.